and it's presented on behalf of the Modeling and Remote Sensing Technical Committee. As you may be aware, the GRSS has got several technical committees, and the Modeling and Remote Sensing MIRS, shown here are the several technical committees, and MIRS is one of our technical committees under GRSS, and I'm the technical chair for the MIRS TC. Our co-chairs are Dr. Rob Sundberg and Jean-Philippe from CESBio France. And today we have the first ad hoc webinar on behalf of the MIRS Technical Committee. MIRS basically addresses electromagnetic theory and optical and microwave modeling, and focuses on techniques that predict for a given remote sensing observation what the product or the observation should be related to the parameters in the modeling space. So without wasting a lot of time talking about the MIRS TC, I'd like to welcome Dr. Alexander Burke. He's a principal scientist at Spectral Sciences and has kindly agreed to give the webinar on MODTRAN band model radiative transfer. For joining the MIRS TC, I just want to give a quick advert here. You're welcome to go look at the website. It's under GRSS, and if you browse through the technical committees, you'll find the Modeling and Remote Sensing webpage, and you can go in and fill out a form and join this committee. If you have any questions regarding the MIRS TC, please feel free to email me at sharmila.padmanabhan@IEEE.org. Just a brief introduction of Dr. Burke. If we go to the next slide. Here, Dr. Burke has served as the lead developer of the MODTRAN model, radiative transfer model, since its inception over 3 decades ago. So it's a great honor for listening from him about the MODTRAN model and learning more about it. So thank you very much, Dr. Burke, for agreeing to give this talk. And I'd like to pass on the controls so he can share his slides. And please use the chat window if you have any questions. We'll try to stay on top of it. If you want to start sharing your slides, and or you're on mute, so want to unmute yourself.
Okay, I should be unmuted.
Excellent. Take it away.
Do you see the screen?
Yes.
Okay. So before I begin, I want to thank Dr. Sharmila and from NASA Jet Propulsion Laboratory and the Geoscience Remote Sensing Society for giving me this opportunity to talk about my favorite subject, which of course is MODTRAN. This talk is being given as part of a remote sensing series, and so I will be describing aspects of MODTRAN which has enabled it to become widely accepted model for this community. And how do I progress slides? Oh, there we go. Okay. In the announcement, when I was first asked to give this presentation, I forwarded my bio. And then when the announcement came out, I saw that the bio was inserted as an abstract. So I thought it would be only fair that I actually begin with an abstract. I'm not going to read the whole thing, but I'll read the red part. Statistical methods were introduced to enable broadband and molecular transmittances and radiances to be computed without explicit monochromatic sampling. For over 3 decades, Spectral Sciences, working in collaboration with the U.S. Air Force, has been fine-tuning these statistical methods within their MODTRAN software, narrowing the spectral band resolution and improving accuracy. the current band model transmittance algorithm will be described. So first, an overview of MODTRAN. MODTRAN generates line of sight transmittances, radiances, fluxes, and more using its statistical band model and correlated K methods. For MODTRAN6, a line-by-line option was introduced for quantifying the accuracy of these statistical methods for one specific applications. You can select your desired resolution or have the code convolve the spectral data with your instrument spectral response functions. The atmosphere is modeled as stratified, right, defined by vertical profiles. The one exception is that MODTRAN does allow you to model a localized gas plume. The discrete ordinate method first introduced by Chandrasekhar is used to model scattering. Atmospheric correction data such as spectral diffuse transmittances and spherical albedos are also generated. Atmospheric paths are modeled, treating the atmosphere as locally spherical and with refraction. This is what we call the MODTRAN poster. It illustrates the key sources, extinction sources for a nadir path through the relatively dry mid-latitude summer model atmosphere. Of note here is the extinction due to particulates, the clouds and the aerosols, and the molecular scattering do not exhibit strong spectral structure. Extinction coefficients adequately describe their narrow band attenuation. However, statistical models are required to characterize the spectral band transmittance arising from the molecular species. So on the center top plot here, I show the location and strength of 32 methane lines at 296 K and a pressure of 1/10 of an atmosphere. As shown on the right, these lines get broadened due to molecular collisions, producing a Lorentzian line shape that falls off as 1 / frequency squared. On the left, you see that the kinetic temperature causes the motion due to kinetic temperature causes us to see a Doppler shifting of the line positions and a Gaussian line shape. Both of these effects occur simultaneously, producing a Voigt line shape shown on the bottom. The band model needs to predict the total absorption, the area under the curve, without explicitly summing the contribution from each molecular transition to each spectral point. That is the purview of the line-by-line methods. The band model methods are designed to provide us an accurate answer, but without the time-consuming line-by-line treatment. So what do we have to do? Here I describe the challenge in a little bit more detail. The question is whether we can define a set of temperature-dependent parameters that define a distribution that looks like and behaves like the true distribution of lines and their strength in an interval. But that alone is not enough. The resulting distribution has to be of a form so that we can calculate the total area under the curve in a single step without having to do the spectral sampling. So we need to define parameters that define a distribution similar to the true distribution and that allows us to calculate the transmittance in a spectral bin in a single step. That's the challenge. Before I describe that, I want to point out that I need to point out that unlike most band models, MODTRAN partitions the absorption from molecular transitions into line center, tail, and continuum contributions. So in this figure, I show, though, the absorption from the 32 lines in our 0.1 wave number interval, and I show their tail contributions. They're bleeding into the neighboring bins. Both the line tail and continuum contributions vary smoothly and can be modeled explicitly. The role of the band model is to enable us to model the total absorption due to the lines centered within an interval. This is really the key slide of the presentation. MODTRAN statistically models the line center molecular absorption as arising from n randomly distributed and identical stronger lines of strength S, S, and NW randomly distributed weaker lines of strength SW. On the left, I show you the sums of the line strengths as computed from HITRAN, raised to the 1/3 through 4/3 power for all the lines in a particular interval for specific species and over a grid of temperatures. We calculate those sums. Then we assume that these can be approximated by our group of strong and weak lines, and calculate those sums as shown on the left in the equations. And when we so we now have 4 equations and 4 unknowns, which we can solve explicitly. And in this particular case, where we started out with 32 methane lines shown on the left, they are MODTRAN estimates this distribution as arising from 4.7 lines of strength 5.1 times 10 to the minus 4th and 17.1 lines of strength about 2.5 times 10 to the minus 5th. The figure on the right is just an illustration. The 4.7 strong lines are assumed to be randomly distributed within the interval, and the 17.1 weak lines are also assumed to be randomly distributed in the interval. And this is really key. One of the scientists best known for being among the first to postulate the influence of man's activity on the influence of climate, a radiative transfer researcher, Gilbert and Plass, also showed that the transmittance due to n randomly distributed lines within an interval is simply equal to the transmittance of a single line within that interval raised to the nth power. So this formula allows us to quickly write out what the transmittance due to our n strong lines and ns strong lines and n w weak lines is. It's just the product of the 2 powers as shown in the bottom here. The final step we need to put together to calculate the transmittance to the random lines is to figure out what the transmittance due to a single line is. Early band models did this using approximate fits to the total absorption in the line, in an interval as a function of the column amount. Those methods did not work when the resolution of the band model was lowered to, or raised, I should say, to 1 1/10 wave number. So we've derived an exact expansion in terms of modified Bessel functions, and this is how the single line transmittance is calculated within MODTRAN. So what does it all mean? Well, the way we test how well a MODTRAN, a band model works is by looking at what's called the curve of growth. How does the total absorptivity, 1 minus the transmittance, vary as the column amount of material increases? In the black and red curves on the right show you a comparison of the true line-by-line curve of growth for our target spectral bin and species methane, and the MODTRAN prediction. The curves look to be in fairly good agreement, but actually this is not perfect. At a column amount of 30 atmosphere centimeters, the difference in the two curves is about 0.03. That's a rather significant error in your transmittance. Why is that happening? The reason it happens in this particular case is that we've assumed that the strong lines are randomly distributed in the interval. If you look at the actual positions of the lines in this particular case, the second strongest line shown in the left, close to 3000.1 wave numbers, is very close to the spectral bin edge. Not what you would expect from a random distribution. It's rather an anomaly, and that anomaly basically means that assuming it's random, we get much more absorption. We get more absorption than the true curve, and that's where we get our error of 0.03. What's important here is that MODTRAN is a statistical model, and being such, it will on occasion misrepresent the curve of growth as shown here, and can lead to errors of a couple percent in your transmittance. This is really the reason why we advertise the 0.1 wave number band model resolution as being 0.2 wave numbers, because doing that smoothing helps smooth out these possible errors. But in general, the fit of the band model to the band model curve of growth to the line-by-line curve of growth is excellent. I know I've gone very quickly, and I hope not too quickly, but my time is running out. I have just the 2 more slides. I've only taken this short period to show how we're able to calculate an in-band transmittance without having to do a line-by-line treatment. But there are a number of other issues and problems that arise when you try to solve the radiative transfer equation in a spectral band rather than monochromatically. And here I'm just listing other issues that if you were to take the MODTRAN training course, these would all be discussed. But as I said, today I only had time to discuss the one. I will highlight the very last item because it is my current pet project, that there is we said early on that we are using a void line shape function when you're working in the microwave and longer wave length, the void line shape function doesn't work well. The void line shape has 3 parameters, the strength and the Doppler and Lorentz half-width. I'm currently working on introducing a 4-parameter spectrally universal line shape function. That's, as I said, that's my current pet project. And finally, I need to just to say a word about validation. As I mentioned up front, MODTRAN6 introduced a line-by-line model algorithm into the model. And what's unique about the way MODTRAN does its line-by-line calculation is that it uses this line center and line tail contribution separation and solves the radiative transfer equation separately in every tenth of a wave number spectral bin. The challenge with such an algorithm, when each tenth of a wave number calculation is separate, is ensuring that you don't end up with spectral discontinuities at the spectral bin edges. In the chart in the upper left, I show the line tail and the line center contributions from each of the spectral bins, and you can see that the individual contributions definitely have discontinuities that are significant, but when you add up their contributions, the top curve has a smooth transition across each of the edges. And so we were able to successfully solve the problem of having a smooth transition between these independent spectral bin calculations. Continuing counterclockwise, the bottom 2 charts show residuals between MODTRAN correlated K calculations and the line-by-line method. So a statistical to the line-by-line comparison. For average resolutions, these residuals are extremely small. The final chart on the right, on the top upper right, shows the comparison between in the long wave through mid wave of brightness temperatures predicted by the correlated K and the line-by-line. There are 2 spectral bands where MODTRAN has traditionally had difficulty with the modeling for a number of reasons. Those are the 15 micron band around 600, near the 640 wave number point, and the that's CO2 band, and the 9.6 ozone band shown around 1,000 wave numbers. Other than that, the residuals are quite small. So with that, I'd like to conclude and thank you for your attention. Any questions?
Thank you, Dr. Burke. And I have a quick question. This is Sharmila. So have you done any modeling beyond 15 microns, like, or is that really the—
Do you mean longer wavelength?
Longer wave. Like I'm working on pre-fire where we are measuring from 4 to 54, so going in the far IR. So I'm wondering if you have done any comparison studies for MODTRAN with the far IR measurements, maybe from series or any other broadband. Actually, you don't have spectrally resolved measurements in the far IR, but yeah.
So the answer is yes. We we state the spectral range of MODTRAN as being 0 to 50,000 wave numbers, and we have done some comparisons between measurements and MODTRAN predictions in the microwave. Currently, my current effort of improving the line shape function really is based on my observation that when we started doing line-by-line calculations at very long wavelengths, the line shape functions that we are using and that many others use in the microwave really I found did not work out well. And so I am working on trying to develop this new line shape function that I believe will be spectrally universal. So if you're working in the radio frequencies, you really want to use a line-by-line method, and I would not suggest using MODTRAN's line-by-line predictions in that region. But if you're in the microwave, I feel confident the MODTRAN results are good.
Mm-hmm. Also, there was one thing I wanted to ask you. I think down in slide before 5 or 4, there was a absorption curve that you had shown for a particular slit number. How is that very specific for that triangular slit? How does it change as you change the dimensions of the slit?
Do I have the right slide?
You're not sharing at the moment.
Oh, yes, I'm sharing. Screen sharing has stopped as the window is closed. Okay, so I have to share again. Okay. You see my commented slides now. Is this the slide you're talking about?
I think slide 4, one before that.
That was the...
Yeah, so see how you write on the side there, mid-latitude wind tornado from space, 12 nanometer, full width half max triangular slit. So you have to recalculate this if your slit dimensions change. Is that what you're trying to say here?
There is a seldom used option in MODTRAN to not have to redo the calculation if your slit function has changed, that the data is saved. I think it's probably been 15 years, if not 20, since somebody's asked me about that option. If you're going to look at a different slit function, people typically find it easier to just redo the calculation. That's not usually a production run. That's usually, you know, during your setup that you're trying to do such a calibration, and reusing data doesn't seem to be necessary. But so there is such an option. It's seldom used, and I'd have to look it up to see how it works, but yes, there is an option to not have to recalculate your slit function.
Okay.
But basically, what a lot of people will do is do that calculation on their own. So when you put in a slit function, MODTRAN also stores the raw band model resolution data. And so if you want to do your own convolutions, people do that also.
Thank you. Other questions?
I have a question, please.
Yes, go ahead.
Hi, Alex. This is Nimrod Carmen. Very interesting talk indeed. I have a question about the band model resolution, and you mentioned that the 1 centimeter is more like 2 centimeters because it's a sort of a random distribution. And I'm asking, in terms of lower resolution instruments such as AVERS and AVERS-NG, what is the optimal band model resolution to use in case we have such wide channels in the instruments?
Well, I can only tell you that my colleague, Steve Adler-Golden, typically uses the 5 wave number band model when he's doing AVERS calculations. I suspect you could push it using our broadest band model, the 15 wave number, but the 5 wave number seems to be what he's settled on over the years. Occasionally he'll run the one wave number, but it generally doesn't make that much difference. So with regard to avarice, it's 5. Again, the reason we added the line-by-line calculation is to allow people to make a choice and then run the line-by-line to determine what the residuals are due to the statistical nature of the model. And if the residuals are not problematic, then you've made a good choice. But it's so application dependent. There are no general rules. In MODTRAN 5 manual and prior, we used to keep general rules about the accuracy of the code, and that they turned out not to be very good. It's really best to take the time to do 1 or 2 line-by-line calculations for your application and determine how best to run your cases. Does that answer your question, Nimrod?
Yes, thank you.
Other questions? Okay, well, thank you very much, Dr. Burke. Irina, do you have any closing words?
No, thank you very much, Mr. Burke, but also Sharmila for this presentation. I think this was giving a very good and overall overview what this committee is doing, and specifically really in the modeling and remote sensing, so that's very important. I'd just like to make the announcement that for next week we have another technical committee that is also at the same time. Different link. The announcement is sent out, I think, or will be sent out tonight.
Okay. Well,
later the day. No.
And I might say that if anyone would like the annotated slides, if you send me an email to lex@spectral.com, I will forward them to you. Thank you very much.
And
Thank you.
This is also giving